This is covering section 5.2, starting on page 55 of your course notes. We're going to be discussing relative extrema. In your notes, starting this section, we are talking about relative extrema. So it says f of a is a blank. So if we look at the graph, remember f of a is like our y value or our function value at the x value a. So if we look at the graph here, a is our x value, and you can see mapped at the top where our y value is. Now, this is called a relative or a local maximum. We're going to use the word relative mostly in this course. And it says since f of a, so the function value at a is greater than the function value for all other x values in the area, right? So looking at the graph, you can see that our y value is just higher than all other values in that area. Okay, it kind of looks like a hill, and we could call it like the king of the hill. Okay, it's the highest value in the region. So relative, local maximum. Likewise, f of b, if you see where b is on the graph, we have a downhill area where our lowest y value, again, in the region, not for the entire graph. As you can see, our endpoints are going to positive and negative infinity. So it's not the lowest or the smallest y value for the entire graph, but just for the region. So again, we would call that a relative or local minimum. Okay, so the function value at b is less than the function value for all other values close to that. Again, that's a relative term, but you can see in the graph what we're talking about. The last graph, it continued on forever in both directions. The first example, right over here, 1 minute, we have a positive slope, and here on the other side of our relative maximum, we have a negative slope. So we can see that we are switching signs in slope, which can also help us find a relative. Okay, this behavior can also occur at endpoints. Okay, I shrunk down the picture a little bit so we can see it better. Okay, so you see in this graph, we have two bold blue circles that are endpoints. So instead of continuing on, like this one has an endpoint. Okay, so it says f has a relative extremum. Extremum. It's supposed to have a T in there. Extremum. At x equals c, if c is a critical number of f of x, remember we talked about critical numbers in the last section, or the last week, or an endpoint of the domain. Note, the converse is not necessarily true. If c is a critical number, it's not necessarily a relative extremum. Okay? But f has a relative extremum if it's a critical number of f of x or an endpoint of the domain. Go back to the maximum. So let's look at an example. Now, if you remember before, we found critical numbers by setting the derivative equal to 0, solving for x, and then using those on a number line to determine where a change in the sign of our function occurs. So in the sign of our derivative occurs, okay? So if our derivative is switching from positive to negative, it might indicate an increase in slope, switching to a decrease in slope, which would tell us possibly where a relative max is. Okay, so in this example, they're saying f of x equals x cubed, looking right here, and the derivative is 3x squared. When we set that equal to 0, we get x equals 0 being a critical number. However, when we check the function values of the derivative at either side, we see that we have a positive slope on either side of 0. Okay, so this means there's no change in slope, so there is not a relative extrema, even though we have a critical number. Okay, so critical numbers are potential candidates for relative extrema, but are not necessarily true. So you can go back to section 5.1 if you want to review a little bit of what we are discussing there. Okay, now we are on page 56 of your notes. So for f of x equals x cubed plus 3x squared minus 24x plus 2, find the x values of all points where the functions defined have any relative extrema. Then find the values of any relative extrema. So we want to first set this equal to 0, find the derivative, set the derivative equal to 0 to find any potential critical points, plot them on the number line to see how the slope is changing, and then identify from that number line and the changing slope whether we have relative extrema. So if we look at the derivative, we get 3x squared plus 6x minus 24. Now we notice that all of these terms are divisible by 3. But first, I guess we have to set our function equal to 0. I'm getting ahead of myself. And then they're all divisible by 3, so we can divide both sides by 3, getting x squared plus 2x minus 8. Okay. Now, remember, so we found our critical points by finding the derivative, setting the derivative equal to 0, and now we have to solve for x. So you'll get 0 equals x plus 4 times x minus 2. 4 times negative 2 is negative 8, and then 4x minus 2x is positive 2x. So our critical points, or potential critical points, are negative 4 and 2. Okay, so we want to check some values in the derivative on either side, to the left of negative 4, in between negative 4 and 2, and greater than 2, to see what our slope is like in each of these regions. So if we plug something into the left of negative 4, say negative 5, we will get a positive number. You can check that on your own. So we have a positive slope for the values that are less than negative 4. If we check in between, so again, pick something easy, check 0, we plug it into our original function, we would get negative 24, which is negative, so these values are negative in between negative 4 and 2. And then we check something greater than 2, say 3, and we will get a positive number. So the slope greater than 2 is positive. Okay, so now if you're thinking of a graph, a positive here would mean our slope is increasing, negative our slope is decreasing, and then it's increasing again. So you can see, if you can picture this in a graph, our relative maximum would be at x equals negative 4, and our relative minimum would be at x equals 2, right? Okay, now it also says to find the values of the relative extrema. So we want to find the original function value of each of these. So the original function value, not the derivative, but the function that was originally given to us at negative 4 is equal to 82. So that's the extremum value in the area. And the function value at positive 2 is equal to negative 26. So that is the relative minimum. And you can check these values if you would like. Okay, our next example. It says for f of x equals x minus 1 over x, find the x value of all the points where the function defined have any relative extrema, then find the values of the relative extrema. So the same instructions as our last example. So first we want to find any potential critical points, so we find the derivative. The derivative of x is just 1. And the derivative of negative 1 over x, remember, think of this as x to the negative 1. So the exponent comes in front, and we decrease the exponent by 2. So that would be like negative 1 over x squared. So that means our sign is switching, right? Negative, we have a negative in the original function, and this one is also negative. So our sign switches. Okay, now notice that this will never be equal to 0, right? X itself can never be 0, right? Because we cannot divide by 0. So therefore, there's no other x values that would be possible critical points, okay? So also notice that this is undefined at 0, okay? But again, 0 is not in the domain. Our domain would be from -infinity to 0 and from 0 to infinity, but not 0 itself, right? Because of this x in the denominator. So since our potential critical point, what's not in the domain here, x can't be 0, but that's not in our original domain, so it can't be a critical point, okay? Now, you could check around 0 and see that there's no change, so that also would show you that this is not a critical point. So there are no critical numbers and no relative extrema. Okay. Our last example for this section says for s of t equals -16t squared plus 40t plus 3, s represents the height in feet above the ground a cork is t seconds after being released when a bottle of champagne is shaken and uncorked. How high will the cork go and how long is it in the air? Now you will see other examples like this where object projectile, so it'll go something like this, right? So the object will project, it will go up with the force of which it's shot at, and then it will fall back down to the earth because of gravity, okay? So in order to find our relative maxima will be in this region, right? At the top of the curve, the maximum height it will get. So we take the derivative of this function. I'm not going to take a lot of time to show that, as this should be getting easier now. But then to find our critical points or potential points, we want to set this equal to 0. So subtract 40 from both sides and then divide by -32. And if we divide both of those by -8, we should get 5/4. Or if we want to use our calculator, 1.25. Okay? So now we kind of know what this should look like, but we can also still find it on our number line. So here is 1.25. We can check our function value to the left of this. So we could try the derivative at 0. We would get 40, right? Which is positive, as we kind of anticipated by the little sketch I have. And then we could try something to the right of it. So we could try 2. The function value at 2, we would have a negative value, right? So -64 plus 40 is a negative number. Again, we don't really care about what the actual numbers are. We just want to know the slope. So quick math. Okay, so that means we have a relative maximum at t equals 1.25. So it's 1.25 seconds after the cork was shot, okay? And our maximum would be s of 1.25. We're plugging in 1.25 into the function, the original function. And we should get the position of this, the height of our projectile after shooting at 1.25 seconds is 28. And that unit, how high will the cork go? 28 feet. Okay. Now, this is still asking us one more question. How long is it in the air? How long is this in the air? So to find that, it's really asking when will the position of it be back to 0, right? So it shoots off. When will it hit ground or whatever surface we're talking about again? Okay. So that would mean in our original function, so s of t, our original function, when is this equal, the position equal to 0 again? So in order to find that, we want to set that equation equal to 0. So we are going to say our s of t function again is negative 16t squared plus 40t plus 3. We want to set this equal to 0. Now, our coefficients do not have anything in common, so we can't simplify it. But in order to solve this, we would use quadratic formula. So t equals negative b plus or minus square root of b squared minus 4ac, all divided by 2 times a, if you remember that, and that's of a function in the form ax squared plus bx plus c equals 0. Now, of course, our variable is t in this situation. But if we do this, we have negative 40 plus or minus square root of 40 squared minus 4 times our a is negative 16, and our c is 3, divided by 2 times negative 16. Okay, and I'll leave that for you, but we will get 2.57 seconds. Now, again, you will get a negative answer and a positive answer when you type this in. Now, since we're talking about time, we're not talking about negative time, right? We want the end time when it hits the ground again, when the position is 0. So that would be at 2.57 seconds. Okay, now I actually missed a problem on page 57 of your course notes, so we are not done yet. Okay, and it says, given the cost function, C of Q equals 70 plus 16Q, price P equals 80 minus 2Q, and revenue function R of Q equals PQ, which is the product of these two terms. We get 80Q minus 2Q squared. Note the profit function then is P of Q equals R of Q, the revenue minus the cost, which is a lot to write down because I didn't put this in our notes. Negative 2Q squared plus 64Q minus 70. Find the number of items Q that maximizes profit. Okay, we're maximizing profit. So notice that we want to maximize this function. Okay, so to maximize it, we find the derivative and set it equal to 0 to find critical numbers, and then check critical numbers to see if they are a relative, max, or min. So they gave us way more information in this problem than we really needed. It's kind of trying to put a bunch of review here in this question. So we get minus 4Q plus 64. We want to set this equal to 0 to find potential critical numbers. So negative 64 equals negative 4Q. So Q is positive 16. So let's check this. If we check the derivative at 0, we would get a positive number, so a positive slope. If we check something greater than 16, say 20, we get a negative number, a negative slope. So again, we're increasing and we're decreasing. So we can see that this is a relative maximum. So for part A, find the number of items Q that maximizes profit. Well, Q equals 16, which we just found. B, find the price P that maximizes profit. So again, this is not the derivative. This is our original. So this is not the profit function. Notice this is little p, okay, right here. Okay, so P equals 80 minus 2Q. We found Q was 16. So P that maximizes profit, what is this value? 80 minus 32, we would have 48. So that's dollars. So $48 maximizes the most profit. And then part C says find the maximum profit. So that would be this P of Q function. So P, big P of 16 equals negative 2 times 16 squared plus 64 times 16 minus 10. If we plug that in, minus 10, 70. I can't read my own writing there. Minus 70. Okay, so the profit would be $442.